these two bookshelves. Shelf A is perfectly uniform, with every book standing exactly 8 inches tall. Shelf B is a mess. Books range everywhere from 2 inches to a towering 14 inches. Yet if we draw a dashed line across the exact center of their heights, both shelves share the exact same average, 8 inches. But relying only on that 8-inch average completely misses the reality of Shelf B. If you were trying to build a perfectly sized box to ship a book from the second shelf, the average is useless. You'd either crush the tall books or leave massive empty space above the short ones. The mean tells us the central tendency, the expected center point of the data. What it completely fails to capture is how the individual data points behave around that center. To understand the full picture, we need a way to measure the spread. We need a metric for dispersion, something that tells us exactly how far our actual items depart from the center. We start by looking at variance. The mathematical engine for measuring this fluctuation involves taking every single book on Shelf B and drawing a line to measure its exact distance from the 8-inch average. But to calculate variance, the formula squares those distances. So if a book is 2 inches above the average, we record a 4. While this effectively penalizes large outliers, it creates a massive practical problem. Our measurement is now in squared inches, which makes no physical sense when we're trying to measure the simple height of a book. To fix this distortion, we calculate the standard deviation. We simply take the square root of the variance, converting our measurement right back into the original readable units. When those squares collapse back down, they give us a single, highly useful number. Standard deviation is simply the typical distance any given data point sits from the mean. It acts as a translator. It takes the mathematical rigor of variance and turns it into a contextually useful value that you can actually understand and report. Let's see exactly how this works in practice by mapping our physical shelves into a pandas data frame. Here in our code, if we write df.shelfa.var and .std for our perfectly uniform shelf, the output is exactly 0. There is 0 spread because every single book sits exactly on the average. But when we run those exact same functions on the jagged Shelf B, the output is a large number. The math immediately exposes the wild fluctuation hiding behind that neat 8-inch average. Now, test your intuition. Pause the video for a second. Imagine a third dataset, Shelf C, that has a mean of 10 inches and a tiny standard deviation of just 0.1 inches. What does that shelf look like? It looks like a nearly uniform block. Because the standard deviation is so small, we know that almost every item in that dataset sits within a fraction of an inch of the 10-inch center. A low standard deviation proves that your data tightly clusters around the expected value. When the spread is tight, the mean is a highly reliable predictor of the whole group. This reveals the most common trap for beginner data analysts, pulling an average and trusting it blindly, without checking the spread. If a dataset has a massive standard deviation, the average is mathematically correct, but it holds almost no predictive value. You cannot use it to make decisions about any single item in that set. This cheat sheet breaks down the 3 commands to memorize. df.mean gives you the center. The command df.var calculates the spread mathematically, in units squared, and df.std translates that spread back into your original units. Remember, in any analysis you perform, an average without a spread is an incomplete sentence. You must always run both. We've solved how to measure the total distance from the center, but what happens to our analysis when that distance isn't perfectly balanced on both sides? Imagine a completely different shelf. On the left side, you have a massive, dense cluster of tiny paperbacks. Then, stretching far out to the right, you have a sparse handful of enormous, oversized encyclopedia tomes. The data is spread out, but it's entirely lopsided. To measure exactly how a dataset leans, we have to look at our next dimension of statistics, skewness.